will allow us to get going at 2:30. So you can get there earlier and be ready at 2:30. Okay, guys. Well, good morning again. Let's finish up stereochemistry. It's also a handout. I was giving it out on Wednesday, but I then realized since that I sent that to you by email. You should already have that one. Except for the first page. First page is not included in the email. So the green here is the first page of that. The rest of that handout you should already have. Is that right? That was the Alkyne handout. Stereochemistry. Where's Waldo? Where's Waldo? We also have the stereochemistry daily questions. We haven't been looking at those. We don't have a lot of time. You can just consider that extra questions. I could give you a million questions. We're only going to be able to go over a certain number of them. Right? The other questions can be just useful questions for you to be looking at on your own, and then you asking questions. I'm going to try to get this projector fixed here. Where's Waldo? Okay, let's get going. Let's see what we need to do. Let's see if there's any questions at the top. When we left off here, did we do this one? I think so, yeah? I see the plane of symmetry right here, yeah? So the mirror image is going to be the same thing. That compound is not chiral, but we call it meso because it does have two chiral carbons, right? So meso compound, yeah? How about these over here? This is a different type of view you may see. This is a 5-membered ring. 1, 2, 3, 4, 5. But instead of being drawn flat on the board like this, it's like we take that, turn it like this, and then this point here will be forward, right? If it's down, we turn it like this, and then the point is forward. That's sort of how this is like. And then the bromines, well, they're both on the same side. They're both up. If you took this ring and made it flat, back to flat, both bromines would be which way? Forward. They would then be forward. Okay? So that's a lot like having a bromine at the point forward, and then here forward. Okay? But now if we put it in that type of regular view, we can see plane of symmetry better. And do you see a plane of symmetry? Yes, right through here. You see that? So what's the answer for this compound? It's not chiral, but is it meso? Yes, it does have chiral carbons. That compound, that carbon's chiral, that carbon's chiral. This is a meso compound. It does have two chiral carbons, yet as a whole it's not chiral. We found Waldo. How about the one on the right? Well, I can draw this just, if I agree it's a 5-membered ring. Okay, got two bromines. Are the bromines cis or trans? They're trans. One's up, one down. Okay, if I have this up and this down over here, right? Whenever I turn it flat, now this one's forward and this one's back. Okay? These are trans. They're in a 1-2-3 relationship. We can do that here. I'm going to put the temp at the bottom and just do this. What if I just say this one's like this, and this one over here, 1, 2, 3, trans. Now, it may actually be drawn in an enantiomer just for the record, but it's okay. Do you see a plane of symmetry? Well, the only place it could be, it would not be here because you don't have two bromines up there. Is that a plane of symmetry? No, bromine coming forward is not mirroring a bromine coming forward. Not a plane of symmetry. There is no plane of symmetry in this compound. This compound, the mirror image thus is different. This compound is chiral. In the end, you might see some views like this. One thing we might look at is way back. You may not have it. Maybe you do. Is when we looked at alkanes. Do I have that handout? Physical properties. Alkanes. I do have that handout. I'll show you something at the very end there. We have the alkanes, cycloalkanes. When we first looked at cis and trans on rings. Okay. Any questions up top? We may eventually go over those. I may send out a key, but any questions about those? Not answers, but questions. For example, you're trying to do one, but you have a question before you can continue on. Okay, let's look at the bottom. We're ready to go back to alkene reaction. Let's skip the first one. The second one's a little bit more introductory. Question. Give the major product of the following reactions. Show all stereoisomers formed for the major product. Is the product chiral? Is it optically active? Show 2 and 4 in Fischer projections. The products in Fischer projections with phenyl 1 and 2 at the top and bottom. Label them as erythro or threo. Pulling it all together. Okay, we got an alkene, got bromine and water. Ready with such a reaction? What type of product are we going to get? A bromohydrin?
Yes.
So only 2 alkene carbons, one carbon is going to get a what? And the other carbon is going to get a what?
Bromine and OH.
One carbon will get a bromine, one carbon will get an OH. Okay? Well, the bromine and OH, are they added to the alkene in a syn or anti manner? Syn or anti? What type of addition is it?
Anti.
Yes, it's anti-addition. Because you get a, what type of intermediate is formed?
Carbocation.
There's no carbocations here. Carbocations are only formed when the alkene reacts with H+.
Backside.
Bromonium ion. And then the water attacks backside, opens up the bromonium ion. That's why you get anti. Okay? That's all your mechanistic knowledge. Can you show products, stereochemistry, etc., etc.? Okay. Here's my recommendation if you want to take it. Whenever you're doing problems like this, how do you know you're doing a problem like this? First off, if you're asked all these questions, you're doing a problem like this. Fischer. You're only going to be asked for this in certain cases. It's when an alkene basically has 2 propyl carbons. That is, ultimately, both of these carbons are going to become chiral. Okay? A real simple alkene like that, this carbon may become chiral in the end, but that one never will be. Because that one's got 2 H's on it already. And if you add something else, it's still going to have 2 H's. And it will still never be chiral. So only one of them is considered prochiral. Potentially prochiral. Here you have 2 that are potentially prochiral. That's when we really need to do this. But again, if you're asked to draw Fischer, that means we need to be able to do what we're about to do. Okay, here's my recommendation. Turn this guy before you do anything. Right now it's drawn flat on the board. Everybody get a handout for that? Anybody have a piece of paper? I got one. Flat on the board. Okay, boom, 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 boom. Phenyl 1, phenyl 2. Flat on the board. But I'm going to turn it and do like this. When I do like that, tell me what do phenols do. Do they go towards you, back, one way, one the other?
Forward.
I know you can't see it, but they're both now coming towards you. How do we draw it like that on the board? Well, you can do it the same way, and I'm going to make this straight instead of slanted. Let's just draw these phenols as if they're coming forward. Now what happens to this methyl when I turn it flat?
Goes back.
It's going back. Okay? So all I did is turn this. Now here the alkene faces forward or back. If I do it like this, now the alkene faces up or down. Okay? That's what it is. It's either up or down. All I've done is turn my molecule, but very powerful. Now I have projections that are going to be useful in the end. Now, regiochemistry of the bromohydrogen. See, mechanistically, which carbon is the bromine going to end up on? And the OH. Because, choice, bromine on the left carbon or over here? Right. Bromine will end up on the right carbon because bromonium ion. But let's go through it, because let's do mechanism. Now, I'm not going to do every little arrow mechanism, but I'm going to just show intermediates. For example, maybe we need to. Then the bromine is here. Maybe we should do it. It's now like this. The bromine's up here. This comes and attacks the bromine up, kicks that off. Well, we could back bond, but I've always did it. So this becomes straight up now. And this is cation. Let's do cation. But importantly, these are still just like that. We have that stereochemistry already there. Straight up. But then this guy back bonds. And by the way, we know this is not actually formed, right? Because this next step is really not as separate. It happens at the same exact time, right? This back bonds. But now what's it going to look like? Boom. Straight up. The back bond is thus straight down like this. Ultimately, they're both up. That's now positive. But we still have our stereochemistry already from the beginning. Phenyl 1 and phenyl 2. Because nothing changes. That's one step. Boom, bromonium ion. Boom, boom. It's all at the same time. There's no chance for anything to change. There you go. There's your bromonium. Now the water comes in. Which carbon is it going to attack? This one. The same place you would have made a cation. But we know it's not really a cation. It attacks here. The bromine bond is straight up, so how does the water come in? Straight down. Kicks that off. And what does that give? I'm going to lose the proton, okay? I'm going to skip the mechanistic step. You should not skip that on any mechanism, but okay. Ultimately, what we're going to get is, boom, this bromine opens up straight up, but the OH is going to be straight down. It comes in straight down. These guys are just pushed up a little bit to make room for this. But the phenyl is forward. The water comes in from here. It pushes it up, but it's still forward. It's just like that instead. The phenyl is up. Phenyl 1. The methyl is also there. And this phenyl here, we're not drawing the H, that's phenyl 2. And there's your product. There's your bromohydrogen. Plus what though? Because, is this compound chiral? Yes, we can prove that by Fischer projection. But you're also going to get an enantiomer because this is chiral. You gotta be careful because on the quiz some of you said plus enantiomer, but your product wasn't chiral, so there is no enantiomer. But this is chiral. Why do we also get an enantiomer? How do you get an enantiomer? The enantiomer comes from, instead of the bromine approaching from the top, it approaches from the bottom. And you repeat everything the exact same way. Instead of going through it, I will just draw this. I'll draw it a little smaller. I should have drew that higher. The enantiomer will look like this. First off, the bromonium would have been down. The water would have came in from the top, opened up, the bromine ends up down, and the OH ends up up. But none of your projections change. And so the methyl is still back, and the phenyl is still there, phenyl 1. And then over here, the phenyl is, we can sort of move it. It is tetrahedral, so it's going to be tetrahedral. We can't draw everything sort of down into here. 2, and you're going to get that. Is that the enantiomer? Well, it is. If we do R and S here, that's going to be switched, and that's going to be switched. That's how you get the enantiomer. And here's a little free information. Any reaction we do now that gives a Kyle product has to give the enantiomer as well. You're never going to do a reaction right now where you only get one enantiomer. Okay? Just know that. It would take time to explain it. But at the same time, not every product is chiral. Okay, now let's put this in a Fischer projection. Any questions here so far? But do you see how powerful it is just to turn this first? From there, everything, all your projections are set. Okay, Fischer projection. Let's do the up here. Okay. OH. Things in the plane, top and bottom. Let's stand here and look through there. Okay, I'm hovering up there. With the OH going away, I'm up here, the OH is going away. What side is the phenyl on? Phenyl 1. I'm up there hovering. Phenyl 1 is it's on my left, correct? If you were up there and the phenyl is going that way towards you, left. So the OH going away, phenyl 1's on the left. With the OH going away, phenyl 1 is on the left. What's on the right on that carbon? The methyl. I'm up here, the methyl's going behind the board, dashed back, methyl's on the right. All right? With the bromine going away, which side is phenyl 2 on? Because remember, the things with the projections we put on the sides. Things in plane we look at, with the bromine going away, what side is the phenyl on?
Left.
The hydrogen being back.
With the bromine going away, what side is phenyl 2 on? With bromine going away, phenyl 2 is on the right. The other thing on that carbon is an H going. Okay? Right? Here we are. When we look through there, that carbon, with the bromine going away, the phenyl's coming towards you guys, correct? So if I'm like this, phenyl 2's on my right. Who said left? And why did you say left?
I said left. And if you had turned the stick man the other way, that's how I was looking at it.
Thank you for saying that. You turn the stick man this way. Like that?
Yes.
No, the bromine's coming towards you. You probably, you were down here.
Yeah, down there. flipped around. Yeah, that's how I was looking at it.
Like this.
Yes,
With bromine going away, phenyl is that way.
yes,
But you got your feet in the air.
obvious.
Because where's the ground? This guy's standing on the ground. The ground is down here. Your feet are up, you're upside down. All right? Because we're drawing, if you call that A and B, A is with the OH, A and B, which one's closer to the ground? B. We're drawing B closer to the ground. So we want to look at it and make sure B is closer to the ground. So the ground is here. You feel on the ground. You're upside down. Thanks for saying that. That's very important. There we go. There's your Fischer projection. Okay, but the question asked, is the product chiral? Well, let's determine that in the Fischer projection. Show it in the Fischer projection with phenyl 1 at top and phenyl 2 at the bottom. Do I have phenyl 1 at the top and phenyl 2 at the bottom? No. Well, guess what, guys? It's okay. Draw it like this first, because the things in your projections go on the side, the things in the plane go at top and bottom. That's the way I've been doing it. But once you get it here, we can rotate. These three can rotate just like a clock. We can just turn the phenyl up here, and we can redraw it. If the phenyl 1 goes up there, it's like the OH is going to be here, and the methyl will come over here. Down here. If the phenyl 2 is at the bottom, bromine's going to come here, and the H will swing over here. Okay? We can just do that. Bromine green. OH blue, like water. How about that? We originally had the OH, phenyl would be black. OH at the top, with the OH at the top going back, the phenyl's on the left. Down here, with the bromine going back, phenyl is on the right, so we got to make another enantiomer. OH and bromine back, phenyl's on opposite side. Pretend that's a methyl. We'll make the methyl gray. Okay, but these three can just spin. Yeah, and as you spin, the OH is back. Here's the phenyl over here. If we make the phenyl back, now the OH is on the right. Phenyl back, OH is now on the right. But the gray methyl moved over here. So you can just spin those three. What you cannot do is start doing a lot of this. You'll end up with a mirror image. We just spun that down there. There you go. There it is in the Fischer. Now we can look for planes of symmetry. Much easier. Do you see a plane of symmetry? Here's where you're pretty much all you need to look is right through there. Is that a plane of symmetry? No, bromine's not mirroring bromine. There's not even a bromine up there. There's no plane of symmetry. So it is chiral. Is it a retro or 3O? High priority groups, bromine and OH, yeah. So it's what? 3O. Is this product from this reaction optically active? But be careful about that question. Or maybe you want to clarify the question. Is this product optically active? Is the product from this reaction optically active? Why do you say yes?
Because it has an enantiomer.
Correct. What's going to be the ratio of these two?
It's on the mixture, you know.
The bromine can attack from the top of the plane or the bottom. Is it going to be 50-50, or is it going to be 90-10, or what?
You want me to make something up?
What?
You want me to make something up?
Well, what do you think it would be in
50.
chemistry land? It's going to be 50-50. Because you've got 1 billion molecules, and they're all around this reagent. 50% of the time it's going to attack from the top, 50% of the time it's going to attack from the bottom. And it's going to be 50-50. Now you may ask, is it going to be exactly to the number 50-50? It's going to be so close that you ain't going to be able to tell any difference. And we call it 50-50. Because when we call it 50-50, that's just one sig fig. I'm not calling it 50.00000 to 50.0000. 50-50 is enough, and it will be 50-50. Because you get attacked from both. You get a racemic mixture. This reaction gives a racemic mixture. So will it be optically active? No, racemic mixtures are not optically active. You got to be careful about the question. Each individual enantiomer is optically active, but this reaction gives a mixture of the two. Okay, now if you drew the enantiomer in a Fischer projection, and you go through this, guess what? You're going to get the mirror image of this. And I'll go ahead and tell you, what you should do is just do it on your own, but here's the product. The other one is going to look like this. Here's your enantiomer. Everybody agree that's the enantiomer of this? Did I draw it right? Those are enantiomers. So if you do draw out the enantiomer, you can do it for practice. We got it right here. If you turn this into the Fischer projection with funnels at top and bottom, it will look like this. Mirror images. They're both 3O, because the mirror image of 3O is 3O. Okay. In the end, at least 2 main things here. Turn your alkene first when you're doing these more complex stereochemistry. And also realize that just because it told us to put phenyls at top and bottom doesn't mean we have to do that at the beginning. Because we can rotate our Fischer projections. What you can't do is start moving methyl over here. If you do, if you make disconnects, you're going to end up with an enantiomer. You also can't do other rotations. You got to be careful about it. All right, questions about that? There are 3 others to work on there. Again, there's a variety of things we could be talking about. Hopefully we'll have a little time to sort of take miscellaneous questions and work on a few. But you really need to be working on them on your own. So when we do talk about them, you're able to ask pointed questions and also get the most out of. Just like you said when we did the lab first and then talked about it, you said it was better. Same thing with working questions. If you work questions first, then when we talk about it, it'll be better. We do need to move ahead because we don't want to run out of time. So I typically save time for questions near the end. We need to move to alkenes. I did want to show you one thing over here though. You don't really need to pull it out. But I did mention, our first mention of stereochemistry was back here. Cis. You remember this when we first showed cis? Both of these are cis, right? But I said these are actually the same exact compound. Do you understand why now? These are mirror images. Again, they're not drawn as mirror images. But if you do RNS, whatever these two are, now been switched. Those are mirror images, but are they the same or different? Well, since we have a plane of symmetry, what does that tell us about the mirror image?
They're the same.
It's the same thing. So that's why I said these are actually the same. But you didn't know what we were talking about back then. Hopefully you do now. On the other hand, these two are different. Mirror images that are not the same because there's no plane of symmetry here. You might look back at that just to confirm your knowledge in the alkane hand gel. Okay. We can try to move on to alkyne chemistry, but any pressing questions? Anything that we left out that we really need to look at right now? How are we doing with stereochemistry? Have you learned anything in the past week and a half? Okay. Again, we need to plow ahead. Green today, summary of our alkyne reactions. So the alkyne has 2 pi bonds. That's good. It's going to be twice the fun. Okay? 2 pi bonds. We're going to do same type of reagents. For example, we can add HX like HBr. Okay? We're going to add across one of the pi bonds. Only one. We'll have one left. But then we can actually react again. Twice the fun. And we can do a double addition. Add HBr twice because we have 2 pi bonds. You can also add like bromine. And we know that bromine adds in an antimatter. Well, yeah. That's the answer to why not Z. These are going to be, this molecule will be E, high priority group's opposite because of the mechanism. But then guess what? You still have a pi bond remaining. We can do it again. So in the end, the chemistry is going to be very familiar. There will be some twists. For example, when we hydrate an alkyne, we add in water across one pi bond remains. With hydration, we only hydrate once. The product called an enol then undergoes a tautomerization, a rearrangement to give a ketone. So actually we'll be able to make a ketone from a hydration of an alkyne with mercury. And then if you hydrate doing hydroboration followed by that magic step, we know we expect different regiochemistry. But when this rearranges, so the tautomerization will be something new. We'll look at the mechanism for it. You guys already know the mechanism. Because the mechanism is going to be basic principles we've already looked at. Okay, so that's an overview. There's some alkynes as drugs. Back. Including a contraceptive, the steroid nucleus. Okay, an alkyne here on the end. Similar to estradiol. Similar to estrogens. Okay. So what I sent you did not include that page. First page of what I sent you is here. Yeah? And we also have nomenclature of alkynes. That was not on the video of the alkenes, so we'll do that here. Nomenclature. First off, all nomenclature is pretty consistent. Just as with alkenes, except we're going to use the YN in yne. Okay, but we'll get to that. First off, terminal versus internal alkynes. This is a terminal. Okay? Terminal. Where the alkene is at the end of the chain. And thus, the N carbon has an H. when it's at the end of the chain, the terminus, the alkyne carbon will just have to have an H. Because if it was another carbon, this wouldn't be at the end of the chain. Terminal alkynes have the CH, and importantly, that's an SPCH, right? Remember the hybridization? That'll be important because we'll talk about the acidity of the H on a terminal alkyne. When the alkyne's in the middle of the chain, it's called an internal alkyne. Internal, or sometimes people will call it a non-terminal. Okay? So that's two different types of alkynes. Basic introductory knowledge there. And of course, your terminal alkyne, your internal alkynes don't have the SPCH. There's no H on the alkyne carbons. Okay, nomenclature. Let's name this terminal alkyne. Longest continuous chain. Well, it's only one chain. 1, 2, 3, 4, 5. Since this is linear, don't miss out on the number of carbons. 1, 2, 3, 4, 5. That's pentane, but we've got an alkyne in our chain, so the pentane becomes what? Pentyne. To indicate we got our triple bond in our chain, carbon chain. But where's the triple bond? Just like with alkenes, you denote the first position of the triple bond. Well, which is the end carbon? Oh, number one. One here or one there? Just like with alkenes, you would want the alkene to be closest to the one carbon. So this is 1, 2, 3, 4, 5. So what do we put in front of this? Yes, 1 pentyne. Does this compound have any stereochemistry? Because in alkenes, it could be cis or trans, or E or Z. Do alkynes have stereochemistry? Are alkynes stereogenic? Could that alkyne be drawn in some other way? The answer is no. The alkyne is linear. You don't have cis or trans. Alkynes are never stereogenic. Okay? There's no stereochemistry there. What do you want to call the next compound?
Heptine. 3 heptine.
Let's see, longest continuous chain. Looks like one chain. 1, 2, 3, 4, 5, 6, 7. That'd be heptane. We got a triple bond heptine. Okay. Heptine. What number do we need to show here for the positioning of the triple bond?
30.
Yeah. Yeah. Do we need any stereochemistry? No. There's no stereoisomer of that compound. What if we put a chlorine here like this? And I drew it as bolded. What's the name of that compound? Six chloro 3 heptine? Or should we change it to 2 chloro 4 heptine? The alkene and alkyne get precedence over numbering. So it remains a 3. You want your alkyne to be at the lowest number before you consider any substituents. Okay? But is that name 100% clear, or is there any ambiguity in here? Can we add additional information to this name? Does this have a stereoisomer? Yeah, this carbon's chiral. I could have drawn that chlorine back. And if I did, that would have been the enantiomer. Which enantiomer did I draw? Now, what do you want to add to your name? Well, this is 1. That's 2, that's 3, H in the back, so this is R. Let's put an R in the front. Now we have a more definitive name with stereochemistry included. Yeah? And of course the R refers to the chiral carbon. What else would it refer to? I think you guys are all with me here. You're just going through it, right? Okay? Now, if I had drawn this bond generically, I wouldn't be able to put anything in front because I don't have enough information. I didn't draw it generically. I drew it very precise. Okay. Reactions. Take this alkyne, react with HCl, we can get such a product here. Well, let's go through the mechanism. This should be pretty straightforward. Pi bond is a source of reactivity, nucleophilic, these electrons. Okay? And I sent you something about mechanisms. You guys are just sort of doing something like this. Okay? A lot of that on the quiz. That's meaningless in multiple ways. First of all, just throwing an arrow towards the acid is not sufficient enough. Also, where's it coming from here? What we need to have is, first off, never work with condensed structures. You can either work with HCl. We'll do that here. Now here, where are we going to leave cation at? Left or right? It's linear, but left or right? Cation over there would be primary. Cation over here would be secondary. We're going to leave it over here. So these electrons are yanked away from this carbon. Let's yank them away. We're using arrows like hands. Grab it and yank it away. We're going to grab right here and yank away. And then this, move over here. This is more precision that's needed. But again, I've also allowed you just to show this ionically if you want. And we can do the same thing and just attack H+. At the very beginning I said either way is fine for me. But just throwing an arrow at HCl condensed is not suitable. So more precision with your arrow movement. What does this give? Okay, it's linear. Let's boom, boom, boom. Now it's going to become a double bond. And now it's trigonal planar, so it's, okay. Which carbon are we adding the H to? Carbon 1 or 2? Which carbon are we adding the H to? Carbon 1. That's why I suspect a lot of you guys are maybe drawing arrows from carbon 1. But that's not showing the electron movement. Okay, but we added it there to carbon 1, and the cation is here on carbon 2, because that carbon is ultimately secondary now. If we had added it here, that would have been a primary cation. But now it's no longer planar. Well, it actually is. Because if you determine the hybridization of that, you'll see that that's still sp planar. So me drawing it bin is actually not correct. But I prefer to do this to get us, because ultimately it's going to become trigonal planar. So then, can you see already how we get that? Hopefully, yes. Then the chloride, if we already have it there, these electrons, okay, boom, and there's your product, right? So this is if you add HCl to this one equivalent of HCl. But guess what? Your product is an alkene. And we know alkenes react with HCl, so we can repeat the reaction. And we will get that over there. But let's act like this wasn't even there. Mechanism. Where are we going to leave cation at? Left or right?
Left.
On the left. Pull it away from there, and we're going to get boom, 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 boom. Okay? The new H on the end. What do you think about this cation we made? It is secondary versus primary. But what do you think about this chlorine there? It's like going to help or hurt the cation? It's not a carbon. We know an sp3 carbon donates by induction. But what is a chlorine going to do here?
Pull.
It's a greedy little, you know what? It likes to pull electrons. It ain't donating. It's greedy. It's electronegative. So is that going to help the cation? No. But it's better than making a primary cation. So it's the same position we predict. But here's something very important. What we have, though, here is resonance. The chlorine actually helps it by resonance. You've got conflicting things here. The chlorine is greedy, but it can help by resonance. And resonance is where we can draw an alternative structure, almost like back bonding, but it's not. These are electrons here. These electrons are going to be attracted down here. And if we did that, what do we get? I'm going to do my arrow like this first. We're going to get boom, 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 boom. There's a new H on the end. But now there's a double bond to the chlorine and a positive charge on the chlorine. This is resonance. This is not a different compound. We have to talk about this. Resonance, and we use a resonance arrow. Resonance arrows are double-headed, not an equilibrium arrows. It's resonance. This is not two different compounds. This is one compound. Okay? What we have here is a compound where a single structure doesn't tell everything about the structure. If you had this cation, are you telling me that these electrons are not going to be attracted towards it? They will be. That's physics. But chlorine doesn't like being positive. Why would chlorine like these electrons? So you got competing things. The true structure here is in between. The true structure is a hybrid. Last thing at this point. We are only moving pi electrons. This kind of looks like back bonding. Everybody agree? But when we back bonded, we made a sigma bond. If you make sigma bonds, you're not doing resonance. You're making a new compound. But this is resonance. We need to be looking at it, building upon it. And here's the end point. Resonance is a good thing. It's stabilized. This is a resonance stabilized carbocation, if you want to call it. But some of the charge has been delocalized. More later. But this is another reason of why the cation's here, even though the chlorine's there. Chlorine's greedy. But it will do resonance. Stabilize your cation this way. But totally different though. How do we get final product? Well, you can see that, right? Boom, we just add here. And that gives final product. The important thing here is that if you do two equivalents of HCl, okay, if we just say HCl 2 molar equivalents, we can go straight there. Do it twice. And what type of product is that? It's a geminal dihalide. Geminal meaning twins. When the chlorines are on the same carbon, they look like twins. We've already seen vicinal dihalides. You made a vicinal dihalide 2 weeks in lab, 2 weeks ago in lab. It was a vicinal. They were next door to each other. Same vicinity. Okay. So that was just twice the fun, but we talked about resonance there. Please be looking ahead. Most of it is, you see how much kind of review or similarities are there? We will pick up a couple of new things, including tautomerization. Please look at tautomerization. Upstairs, is that right? Next